Hello! In this demonstration, we'll learn how to simulate reproduction and breeding in your SPEGG model. Recall the simulation class responsible for running the simulation and its accompanying header file discussed in Video 1. In this video, we'll mainly talk about the next operations involved in simulating reproduction. But before doing so, let's briefly revisit the simulation class. There, we defined a function, run, that will be in charge of actually carrying out the simulation. Back to our CPP file, after your individuals have been initialized, the first thing you want to do is define this run function. Now if you look in the header file for the base simulation class, I'd like to draw your attention to a variable called n_steps. This is a variable that will store the number of time steps you want to simulate in your model. So the first thing we'll do in the run function is to pass a for loop that will instruct our simulator class to run the model. The for loop will repeat for n steps, during which the core of our simulation will take place. The first thing we may want to do after initializing our class might be to simulate reproduction among the individuals in our species. To do this, we'll call our function addKids of the demo species object. Now let's navigate to the header file defining our demo species class. We specified a function called addKids, which we'll now implement in our demospecies.cu file. The first thing you want to do when simulating something like reproduction is actually a bit of bookkeeping using a function called deemCalculations. DeemCalculations is defined in our base ins.cu class, and it counts up the number of individuals in different patches. This is important because when we actually go to add the offspring, we will frequently need to reference the sizes of individuals in various patches. Let's now return to our addKids function in our demospecies.cu file. Let's define an instance of our demospecies parents class, which we saw in our last video, which we'll call example parents. We then instantiate this by calling new and passing our demospecies class as a pointer. Then, we will call a built-in function from the base parents class called setupParents. This function will take care of executing all the calculations needed to determine who our potential parents are going to be, as well as assign them reproductive probabilities. So in this way, we've just called the functionality we just defined in the demospecies parents class. Now the parents class has associated with it a single variable called potential number of kids. This variable notes how many new offspring will result. Needless to say, if there aren't going to be any new offspring, there's no sense wasting more time inside the function addKids. So what we'll do is set up a conditional here. If potential number of kids from example parents is greater than 0, then we'll proceed with the rest of the code for addKids. I should briefly digress here and discuss a point about SPEGG's overall design. For performance reasons, the demo species class has allocated data for all current and all future individuals that are modeled during your simulation. That means you can never simulate more individuals than there is space available in your demo species class. This might seem biologically unrealistic, but it's pretty easy to get around this limit by ensuring, inside your addKids function when we evaluate viability, that density dependence prevents your population size from exceeding the memory allocated to demo species. One implication of this is that the actual data storing the information about the newborns in fact resides in our demo species class. Assuming there will be a reproduction event, we'll want to make use of a class called eggs neonates that keeps track of our, as yet unspecified, newborns and manages their affairs. What eggs neonates does is essentially act as a mediator between the parents class and the as yet unpopulated data in our demo species class to specify the data in the demo species class to reflect the properties of our new cohort of newborns. So we'll define an instance of this class, demospecies neonates, and instantiate it by calling the constructor to eggs neonates. This constructor takes two arguments. First, it needs to know which species object we are creating the newborns for, which is just this class. Second, it needs to know how many offspring each female will reproduce. This is actually stored in a vector that is part of the base parents class called kids per mom. The kids per mom vector was calculated in the setup parents function defined above. Now, to simulate the transmission of genetic information from parents to offspring, we will invoke a method of the eggs neonates class called inherit genotypes. Inherit genotypes takes two arguments: a vector specifying the probability that individuals become female parents, and a vector specifying the probability that individuals become male parents. Recall that both these vectors are members of the parents class. A little bit about what this function inherit genotypes does. A lot of its functionality has deliberately been encapsulated here, so that SPEGG users don't have to obsess about its gory details. But basically what this function does is assign parents to newborns based on their reproductive potential. Now, it can also be modified to permit alternative mating strategies. For example, when you have assortative mating, a version of inherit genotypes will actually assign pairs of parents to newborns. In any event, once the parents are assigned, inherit genotypes will then copy the parents' genotypes to the offspring genotypes. In some species, this will involve mutation of the allelic values as well as recombination among the loci at varying rates. Both these parameters are controlled by the user using an approach we'll describe in our final video. Thus, inherent genotypes makes up the core of the transmission of genetic information across generations in SPEGG. Now that our offspring have genotypes, we will assign them their phenotypes using our familiar setPhenotype function from before. Only this time, unlike when we invoke this code during initialization, we will need to set the phenotypes only for the newborns. Thus, we pass an argument that notes the population size prior to reproduction, which is provided by the eggs neonates class, and a value of the number of newborns, which is given by a value called total number of neonates. These values were set by the constructor when we instantiated our eggs neonates class. Note the total number of neonates differs from potential number of kids. The variable potential number of kids describes the aggregate reproductive potential across females, but the realized reproductive output, given by total number of neonates, can differ from the overall reproductive potential. After the offspring have been assigned their phenotypes, let's assign them their sex using the assign sex function as we did during our initialization. Now we've used up all the functionality of our eggs neonates class, so let's delete this class. This completes our block of the conditional statements. At this point, individuals in different demes are actually not contiguous in memory space. This occurs because data about newborns are stored in memory after the last data point storing information on individuals from the previous generation. Thus, if there is more than one deme, the data on the newborn individual is not guaranteed to have the same deme value as the individual immediately preceding it in memory space. For reasons that are too complicated to go into right now, this can be a problem down the line. So we want to make all individuals from the same deme contiguous in the memory. There are ways to get around having to call sort by deme at this stage in the code. But to belabor the importance of contiguous arrangements of individuals in the same deme, I've held off on implementing those solutions just quite yet. Now the inflow of new individuals into our species class means that we need to update information about the demes in our simulation. So we'll call the deme calculations function once more. Finally, we have already completed our use of the parents class, so we can delete this object as well. And that closes out our add kids function. In the next demonstration, we'll go over the functionality for updating the phenotypic values of individuals in determining who lives and who dies. Thank you for watching, and if you have any questions, please shoot us an email via our mailing list, speg-users@googlegroups.com.